Jai to all. Myself, Mahendra Dwivedi, EN Department, Assistant Professor in AKGEC, Ghaziabad. So today we'll discuss the topic from electric drives with subject code is KEE075. So this topic is taken from Unit 2, and today we are going to discuss about the selection of motor power rating and classes of motor duty. This is one of the very important topic because this is misunderstood by most of the we can say graduate people, like what is the motor power rating which should be selected for a particular application, and why we should look for the classes of motor duty, because each application cannot have same motor. So for a particular application we need different classes of motor duty. So we'll discover all these things in this lecture. So content will be like selection of motor power rating, thermal model of motor for heating, thermal model of motor for cooling, classes of motor duty. So let us see one by one. So selection of motor power rating. Selection of motor power rating of a motor for a specific application must be carefully chosen to achieve economy with reliability. Use of a motor having insufficient rating either fails to drive the load at its normal productive level or lowers the productivity and reliability through frequent damages and shutdowns due to overloading of motor and power modulator. On the other hand, if power rating is decided liberally, the extra initial cost and extra loss of energy due to operation below rated power makes the choice uneconomical. Furthermore, induction and synchronous motors operate at low power factor when operating below the rated power. So this is one of the very important parameter which one should understand, why we should choose the proper motor rating for a particular application. Because in the industry we'll see 70 to 80% motors are induction motor, and when they are operating below their rated power, so they will have low power factor, and we all know what are the consequences of operating at low power factor. So we have to take care about these things. So when a motor operates, heat is produced due to losses, that is copper, iron and friction. Other types of losses are also there inside the machine, and its temperature rises. As the temperature increases beyond ambient value, a portion of heat produced flows out to the surrounding medium. The amount of outflow of heat is a function of temperature rise of motor above ambient value. So as motor temperature rises, the heat outflow increases and equilibrium ultimately sets in when the heat generated becomes equal to the heat dissipated into the surrounding medium. So in coming slides we will see this is also one of the very important parameter. So motor temperature then reaches a steady state value. Steady state temperature depends on power loss, which in turn depends on the output power of the machine. Since temperature rise has a direct relationship with output power, it is termed as thermal loading on the machine. So steady state temperature is not same at various parts of the machine. It is usually highest in the windings because loss density in the conductor is high and dissipation is slow. Since conductors which are wrapped in insulating material are partly embedded in slots and thus are not directly exposed to the cooling air. So let us see, amongst the various materials used in machine, the insulation has lowest temperature limit. Depending on the temperature limits, insulating materials employed in the electric machine. So these are divided into classes. So there are different classes of insulation, and temperature against those insulation is also given, so that one must understand the highest temperature level which can go, and therefore the type of insulation which should be selected for the windings of a motor. So if we will see, this is gamma, so its upper limit of temperature is 90 degree. A type insulation can have upper limit up to 105 degrees, E type 120, and so on. So if we will see, most of the faults in the industries occur due to failure of the insulation. So one must understand the application, what could be the maximum temperature that can be calculated, and on the basis of that the insulation material for winding should be selected, such that in occurrence of any types of fault, the insulation material remains in its original state. It should not melt. And in most of the application, what is happening, when there is some transient condition or there is some fault, so failure of the insulation is there, and due to which there is a short circuit in the motor. When operating for a specific application, motor rating should be carefully chosen to ensure that insulation temperature never exceeds the prescribed limit. Otherwise, either it will lead to its immediate thermal breakdown, causing short circuit and damage to winding, or it will lead to deterioration of its quality, resulting into thermal breakdown in near future. So for loads which operate at a constant power and speed, determination of motor power rating is simple and straightforward. But only a few loads operate at a constant speed and power. Most loads operate at variable power and speed, and the pattern of these variations are different for different applications. So let us see, the selection of motor power rating has three objectives: to obtain a suitable thermal model for the machine which can be utilized in calculation of motor rating for various classes of motor duty, categorization of load variation with time into certain standard categories which are termed as classes of duty of motor, to present method for calculating motor rating for various classes of duty. So this is the objective of selection of motor power rating. So let us see thermal model of motor for heating and cooling. So an accurate prediction of heat flow and temperature rise inside an electrical motor is very difficult owing to complex geometrical shapes and use of heterogeneous material. Since conductivities of various material do not differ by a large amount, a simple thermal model of machine can be obtained by assuming machine to be a homogeneous body. So although inaccurate, such a model is good enough for a drive engineer whose job is only to select the motor rating for a given application, ensuring that temperatures in various parts of the motor body do not exceed the safe limit. So let the machine, which is assumed to be a homogeneous body, and the cooling medium has following parameters at time T. P1 is the heat developed, that is given in joules per second or watts. P2 is heat dissipated to cooling medium, joules per second or watts. W is the weight of the active part of machine in kg. H is specific heat, joules per kg per degree centigrade. A is the cooling surface area. D is the coefficient of heat transfer or specific heat dissipation, that is given in joules per second per meter square per degree Celsius. Theta is the mean temperature rise. So during a time increment, suppose dt, let machine temperature rise be d theta. Since heat absorbed or stored in the machine will be given by heat developed inside the machine minus heat dissipated to the surrounding cooling medium. So this is the heat developed and this is the heat dissipated to the surrounding cooling medium. So if we will see, these are two equations, and rearranging the term, we will get d equal to C equal to WH, where C is the thermal capacity of machine in watts per degree centigrade. D is the heat dissipation constant. So this is the heat dissipation constant, watts per degree centigrade. Heat dissipation mainly occurs through convection. Typical values of D are in range of 40 to 600 watt per meter per degree centigrade. First order differential equation 3 has a solution. So constant integration K is obtained by substituting the temperature rise at T equal to 0 in equation 6 when initial temperature rise is theta 1, and equation 6 has a solution like this. So where tau, which are the dimension of time, this is the tau here, and it is known as heating or time constant of the machine. So in equation 9, as we'll set T equal to infinite means when motor is run continuously. So at T equal to infinite time, theta will be equal to steady state temperature. So this will be equal to steady state temperature of the machine. Thus theta SS is the steady state temperature of machine when it is continuously heated by power P1. So at this temperature, all heat produced in the machine is dissipated to surrounding medium. So let the load on machine be thrown off after its temperature reaches a value theta 2. So heat loss will reduce to a small value P1 dash and cooling operation of motor will begin. So let new value of heat dissipation constant be D dash. So if time is measured from instant the load is thrown off, so this is given by this equation. Solving this first order differential equation subjected to initial condition, that is theta 2. So for first operation when load was connected, so final temperature was like theta 2 and now at T equal to 0 for cooling period, it will give at tau dash equal to C by D dash. So theta dash SS is again steady state temperature rise for new condition of operation, that is tau dash is known as cooling time constant of the machine. If motor were disconnected from supply during heating and cooling curves of the electric drives, then P1 dash, that is the loss, small loss, is equal to theta dash SS equal to 0, suggesting that final temperature attained by motor will be ambient temperature. So equation 11 will give theta equal to theta 2 e to the power minus T by tau dash, that both heating time constant tau and cooling time constant tau dash depend on respective heat dissipation constant D and D dash, which in turn depend on the velocity of cooling air. So in self-cooled motors where cooling fan is mounted on the motor shaft, velocity of the cooling air varies with the motor speed. Thus, varying cooling time constant tau dash, cooling time constant at standstill is much larger than when running, because the cooling fan speed is directly proportional to the speed of the motor. Therefore, in high performance and medium and high power variable speed drives, motor is always provided with separate forced cooling so that motor cooling be independent of speed. This figure shows the variation of motor temperature rise with time during heating and cooling curve. So during heating we can say temperature is increasing and during cooling temperature is coming down. So we can say this is the ambient temperature. This is ambient temperature. Thermal time constant of a motor are far larger than electrical and mechanical time constant, while electrical and mechanical time constant have a typical range of 1 to 100 millisecond and 10 millisecond to 10 second. The thermal time constant may vary from 10 minutes to couple of hours. So let us see classes of motor duty. So it is given in the standard 4722 to 1968 categorizes various load time variation encountered in practice into 8 standard classes of motor duty in electrical drives. So if you will see continuous duty, short time duty, intermittent. This is the basic classification. Further if you will see intermittent periodic can be classified into starting, intermittent periodic duty with starting and breaking, continuous duty with intermittent periodic loading, and continuous duty with starting and breaking. So continuous duty with periodic speed changes. So these are some of the classes of motor duty. As we can see the diagram here, if we will see the load torque is always constant and temperature reaches a steady state value theta ss, and therefore this is continuous duty. So if we will see, this is the short time duty, load torque is for a short period and therefore there is increase in temperature and there is a cooling period. Similarly, if we will see intermittent periodic loading is there, so load is provided to the motor, then shut down from the motor, again loading is there. So if we will see increase in temperature, decrease in temperature, increase in temperature, again like this. So this is intermittent periodic loading with starting. So during starting, high power as well as torque is required, and therefore here we can say this much of torque required. So initially rapidly temperature is increasing. Once it is coming to its normal operating condition, so temperature decreases, and when load is shut down, so temperature further decreases. Similarly, this is during starting as well as during breaking. So if we will see, normally temperature is increasing slowly, and then when breaking operation is applied, then temperature is reducing and coming back to cooling period or cooling temperature. So it denotes the motor operation at a constant load torque for a duration long enough for the motor temperature to reach a steady state value. This duty is characterized by constant motor loss. Examples are paper mill drives, compressor, conveyors, centrifugal pump, fans are some of the examples. So in the short time duty, in this time of drive operation is considerably less than heating time constant, and machine is allowed to cool up to ambient temperature before the motor is required to operate again. In this operation, machine can be overloaded until temperature at the end of loading time reaches the permissible limit. So some examples are crane drives, drives for household appliances, turning bridges, sluice gate drives, valve drives, and many machine tools. Intermittent periodic duty. So it consists of periodic duty cycle, each consisting of a period of running at a constant load and a rest period. Neither the duration of running period is sufficient to raise the temperature to a steady state value, nor the rest period is long enough for the machine to cool up to ambient temperature. So in these classes of motor duty in electrical drives, heating of machine during starting and breaking operations is negligible. Some examples are pressing, cutting, and drilling machine drives. Intermittent periodic duty with starting. So this is intermittent periodic duty where heat losses during starting cannot be ignored. Thus, it consists of a period of starting, a period of operation of constant load, and a rest period, with operating and rest period being too short for the respective steady state temperatures to be attained. In this duty, heating of machine during braking is considered to be negligible, because mechanical brakes are used for stopping or motor is allowed to stop due to its own friction. Few examples are metal cutting, drilling tool drives, drives for forklift, truck, mine hoist, etc. Intermittent periodic duty with starting and braking. So if we will continue duty with intermittent periodic loading. So we have seen, so this is continuous duty with starting and braking, continuous duty with periodic speed change. Thank you.